This is the ELP 101 project. The topic that I have chosen is a gyrator circuit as an application of an operational amplifier. My name is Yadvender Singh and I'm from group number 4. So let's talk about an operational amplifier first. An operational amplifier, or op-amp for short, is fundamentally a voltage amplifying device designed to be used with external feedback components such as resistors and capacitors between its output and input terminals. These feedback components determine the resulting function or the operation of the amplifier, and by the virtue of different feedback configurations, whether we use a resistor or a capacitor or both, the amplifier can perform a variety of different operations, giving rise to its name, operational amplifier. So let's talk about some common configurations of an op-amp. First, let's talk about inverting input. In this configuration, the output is fed back to the negative or inverting input through a resistor R2. The input signal is applied to this inverting pin through a resistor R1. The positive pin is connected to the ground due to the negative sign, as you can see in the formula, Vs equals to minus VE R2 by R1. The output and input signals differ by a 180-degree phase angle. Now let's talk about the non-inverting. This configuration is very similar to the inverting operational amplifier. For the non-inverting one, the input voltage is directly applied to the non-inverting pin and the end of the feedback loop is connected to the ground. As we can see, the input and output voltages are of the same sign in this formula here. Now let's come to the main topic of the gyrator. A gyrator is a two-terminal device based on the op-amp that inverts the current voltage characteristic of an electrical component. Therefore, we can use a gyrator to convert a capacitor into an inductor or vice versa. It is very, very helpful because it can simulate the working of an actual inductor, requiring much less space and cost as compared to an actual physical inductor. These are essentially useful in circuit boards where we have a big space constraint. Since the wires forming an actual inductor offer some resistance as well, we can eliminate the problem by using a gyrator. The gyrator is often described as a fifth linear electrical component after resistor, capacitor, inductor, and transformer. Now, this is how the gyrator circuit looks like. The upper half is the design of a gyrator circuit, and the lower half represents the equivalent circuit that can be used to replace the gyrator circuit. So, as you can see in the circuit diagram, the complex circuit containing the op-amp and capacitor can be replaced just by this inductor here. The inductance is given by the formula RL into R into C. This way we can emulate an inductor without using a physical inductor at all. Now let's talk about the uses of the gyrator circuit. The primary application of a gyrator is to replace heavy, costly, and bulky inductors in electrical circuits. For example, RLC bandpass filter characteristics can be realized with capacitors, resistors, and operational amplifiers without using inductors. This graphic equalizers can be achieved using an op-amp, resistor, and capacitor because of the invention of the gyrator. Gyrator circuits are extensively used in telephone devices that connect to a POTS system. POTS is a plain old telephone set. This has allowed telephones to be much smaller as the gyrator circuit carries DC part of the line loop current, allowing the transformer carrying the AC voice signal to be much smaller because now no DC current passes through. Now let's compare it with the actual inductor. Firstly, speaking about magnitude, physical inductors are limited with the range of magnitude because of physical constraints. Their magnitude is usually limited to the order of 10 to 100 Henry, but using a gyrator, we can emulate inductors with inductances ranging from microhenries to megahenries. Now let's talk about the ideal nature. Physical capacitors are much closer to ideal behavior as compared to physical inductors. And hence, by using a capacitor in a gyrator circuit, we are able to get a much more ideal inductor than we would by using a physical inductor. Talking about energy storage, simulated inductors cannot replicate the energy storage capabilities of physical inductors. This is a drawback. This limits their applications in the power domain. They also don't react to sudden changes by producing a back EMF as an actual inductor. Magnetic properties of simulated inductors don't match up as well. They don't respond to external magnetic field, nor do they create their own magnetic field when current passes through them. So that was it from my side. Thank you.